Hello everyone. This is part 2 of section 16.1. Last time we introduced the del operator, so it behaves like a derivative, but it's an operator again. And when applied, when taking the dot product of the del operator with the function, we get the divergence, and then the curl. Remember the cross product, we set it up ijk, and then there's our del operator and our function. So, it's some questions, combinations of things here. So we're given two vector fields, f and g in this case. This is what we want to find. So, as we know, work from the inside out. We'll first evaluate what's in parentheses. And so, the cross product of f and g will be equal to, okay, so standard setup, I, J, and K. And then F in the first row, Y, Z, X, Z, and X, Y. I said first row, I meant second row, of course. G in the third row, X, Y. X, Y is our J. You gotta be careful there, I guess. So we get a 0 for the I. And the XY is the J, and XYZ is the K. Okay, so then to evaluate that 3 by 3, we call the procedure. So recopy the first column, I, Y, Z, and 0. And the second column recopied, J, X, Z, X, Y. Okay, and then we can take this cross product. Remember, it's going to be, let me do it down here. Okay, we group the i's together, so the I positive diagonal, get rid of this equals, is xz times xyz, so x squared y z squared, and then minus the negative I, xy, so x squared y squared, so that all times I, and then plus the j's, we'll get a 0 there for the positive j, and then for the negative j minus xyz times yz, so x y squared z squared, so that times j, and then plus the k's, positive k's are yz times xy, so x y squared z, and then minus the negative k's are 0. Okay, so if we wanted to rewrite that, f cross g, x squared y z squared minus x squared y squared times I, and then minus xy squared z squared times j, and plus xy squared z times k. Okay, so now the del operator dotted with that result. Okay, if you want to write it out formally, it's really the del operator partial with respect to xi plus partial with respect to y, j, plus partial with respect to z, k, dotted with what we just found. So actually, let me use brackets there since I get some parentheses around the I. In this step, you could basically skip, but I'm just illustrating this formally at least this one time. So here I'm recopying the cross product of f and g. Okay, so just to remind us about the dot product, the fact that we take the I dot i's is 1, j dot j is 1, and k dot k is 1, and then every other that doesn't match are zeros. So we get partial with respect to x of the x squared y is z squared minus x squared y squared, and then plus the partial with respect to y times the negative xy squared z squared, and then plus the partial with respect to z of x y squared z. And now taking those partials, del dotted with f cross g is, okay, with respect to x, y and z are constants, so x squared becomes 2x, so 2x y z squared minus y is a constant here, derivative of x squared, again 2x, so minus 2x y squared. Now the partial with respect to y of this, x and z are constants, derivative of y squared 2y, so minus 2xy z squared, and then the partial here with respect to z, x and y are constants, derivative of z is 1, so plus x y squared. And let's see if that can be simplified. Looks like the these two guys zero each other out, and then we've got a minus 2xy squared plus 1xy squared, which just gives us minus xy squared. Okay, so a couple more examples to finish off this section. And now we're just given one function, vector field, and we want to find del dot del cross f. So we'll start from the inside again. Del cross f, 3 by 3 determinant for cross product. Remember I, j, and k. In the first row, del, the operator, partial with respect to x, partial with respect to y, partial with respect to z for the second row, and then f goes in the third row. That's e to the xy, 3x, e to the y, and e to the yz. Okay, so then repeat the first two columns. I, operator, partial with respect to x, e to the xy, j, partial with respect to y, 3x, e to the y. Okay, so then the cross product. Okay, again, grouping the i's. Okay, now remember, when we do this with the cross product, it's really the curl. You take the partial, you really focus on the partial first. So the partial with respect to y of e to the yz, well, the derivative of e to the yz is e to the yz. So e to the yz times the derivative of yz, which with respect to y, z is held as a constant, derivative of y is 1, so I'll write z e to the yz, and then minus, okay, this negative I is partial with respect to z of this, but x and y are both constants, so that's a 0, so that times I, and then plus, for the j's, partial with respect to z of e to the xy, but x and y are constants, so that's 0. and then minus the negative j's are this column, or this diagonal, excuse me, and that's the partial with respect to x of, yeah, I'm sorry, just found a mistake. This was just recopying mistake and not a big deal right now. This was e to the xz, not e to the xy. So make sure you make note of that. And I apologize. So that does change the 0 here, because we have partial with respect to z of e to the xy. So x is held as a constant. Derivative of z is 1. So 1 times x is x. So x e to the xz. And then minus, here's the negative j diagonal, partial with respect to x of e to the yz. That's going to be a 0 because y and z are constants. And then plus j to the k diagonal, so with respect to x of this. And e to the y would be a constant, derivative of x is 1, so 3 e to the y. And then minus the negative k's, this diagonal here, partial with respect to y, e to the xz are both constants, so that's going to be a 0 times k. Alright, so now if you wanted to just recopy this, z e to the yz times I plus x e to the xz times j, and then plus 3 e to the y times k. And now we need the dot product of, or del dotted with that result. Okay, so you don't really have to show, when you dot del with something, you really don't have to show the literal dot product. It's really just, think of it as the differential operator, del operator, and you're just taking the partial derivatives of each I, j, and k coefficients with respect to x, y, and z partially, respectively. So skipping the literal dot product, partial with respect to x of z e to the yz. I suppose you can even skip this step if you wanted to, but I'm always going to show this one. Then partial with respect to y of x e to the xz, and then plus the partial with respect to z of 3 e to the y. Okay, so then taking these partials, we have z and y are both constants because we're doing it with respect to x, so 0, plus, now we're doing it with respect to y, so x and z are constants, so 0, and now we're doing it with respect to z, so y is a constant, so 0. So that turns out just to be a 0. Okay, one last example for the fun of it. Again, work from the inside out. Del cross f. Set up your 3x3 determinant. I, j, k. The first row, the del operator, partial with respect to x, partial with respect to y, partial with respect to z. Second row, and then third row, the function xy squared minus 3yz and xy. And then to evaluate this 3x3, again, recopy first two columns. Alright, so now we're ready to evaluate that 3 by 3 determinant. Okay, so we get for the i's, partial with respect to y of xy is just x. And for the negative i's, it's this diagonal. Partial with respect, remember we always read from the partial, with respect to z of minus 3yz, due to z is 1, so minus 3y, so that times I, plus for the j's, positive column, or positive diagonal, partial with respect to z of xy squared is 0, minus, because xy squared is x and y are constants. Then for the negative j's, partial with respect to x of xy, that's just y, so that's times j. And then for the k's, positive partial with respect to x of negative 3yz, y and z are both constants, so that's going to be 0. And then we have minus from the k's. Here's the minus column or diagonal for the k's, partial with respect to y of xy squared, or to y squared 2y, so 2xy, and that times k. Okay, and I did make one careless mistake. Hopefully you caught it. When I took this diagonal here for the negative i's, it should be minus a minus 3y. So that should be a plus 3y there. So make sure you make that correction. Okay, so let's just make this look a little prettier. So x plus 3y times I minus y times j minus 2xy times k. Okay, so now we need del crossed with that result. So now del cross f is cross product 3 by 3 determinants again. So I, j, and k. Actually, let me spread these out a little bit more. And the operator del, partial with respect to x, partial with respect to y, partial with respect to z. And then the functions, x plus 3y, negative y, and negative 2xy. So then again, recopy, first two columns, I, partial with respect to x plus 3y, j, partial with respect to y, and negative y. And now we find that cross product. Okay, so for the positive I diagonal, partial with respect to y of negative 2xy, where y is 1, so just negative 2x, then minus, okay, here's the negative I diagonal, partial with respect to z of negative y. Y is a constant, so that's 0, so that times I, and then plus, okay, for the positive j column, we have partial with respect to z of x plus 3y, but x and y are both constants, so with respect to z, that's a 0, and then minus, for the negative j's, partial with respect to x of negative 2xy, so y is a constant, or negative 2x, negative 2, so negative 2y, so let's make this plus 2y, minus a minus, of course. And then finally for the k's, positive k is the partial with respect to x of negative y, y is a constant, so that's 0, and then minus, here's the partial the negative k diagonal, partial with respect to y of x plus 3y. X is a constant, so its derivative is 0, and derivative of 3y is just simply 3. And that times k. Alright, so now we've got it. So I'll recopy partial, or the del operator crossed with del cross f is negative 2xi plus 2yj and minus 3k. Alright, so that's it for section 16.1. We'll come back for 16.2 when you're ready.